Differential equations, we're moving on to section 2.5. We're going to be spending a number of days there. But for 2.5, day 1, we've talked about separable differential equations, linear, the exact, and the almost exact, where we had to find an integrating factor to get an exact differential equation to solve. Today, we're getting into homogeneous functions. And the homogeneous function, we've got a definition right here. A homogeneous function, a function of x and y, if we were to substitute in, instead of having x and y, if we substituted tx and ty, if you could factor out t to a power, and that power here is alpha, as long as alpha is the same degree that we're factoring out from all parts here, and we can get a form t to the alpha times f of x comma y, then we have a homogeneous function. Let me show you an example. Let's say we have this f of x comma y, and we have x to the fourth plus y to the fourth. If I were to substitute in, instead of having an x, we had tx. So everywhere where you see an x, we'll replace it with a tx. Everywhere where we have a y, we'll replace that with a ty. You can see this would be t to the fourth, x to the fourth. This is t to the fourth, y to the fourth. But you can see that we have a t to the fourth in common, so I can factor out a t to the fourth, leaving us with x to the fourth plus y to the fourth. But that's really the same thing as saying t to the fourth times the original function. And right there, because I've shown that that substitution leads to t to a power times the function, this would be a homogeneous function. So this would be a homogeneous function. Where we're going today is we're going to look at a differential equation. It's going to look so much like what we've been talking about lately. We've got m of x comma y dx and an n of x comma y times dy. It's equal to 0. This would be a homogeneous differential equation. And by the way, this is a very special classification. When we say homogeneous differential equation, we now are referring to this form if m, the function multiplied to dx, and n, the function multiplied to dy, are homogeneous functions of the same degree. So in other words, it's not enough to get m and n both to be homogeneous functions. That's certainly necessary. It's just not sufficient. We have to go one step further and show that we'd have the same power factored out, the same degree. If that's the case, then we have a homogeneous differential equation, and then we can proceed with this method of solution. Everywhere where we have a y, we can replace that with ux, possibly. That's one option. If we were to take a derivative, much the way we were working in Calc BC, just with that differential, we'd have dy using the product rule. We'd have u times dx plus du times x, and we'll just move the du back. And we'll be substituting everywhere where we see a y, we replace that with ux. Wherever we have our dy, we'll replace it with this equivalent form. Very similarly, we could also substitute in x equals v times y. And then we could, again, take a derivative and get dx is equal to, with the product rule, v dy plus y dv. Now the big question, of course, is thinking, how do I know which form to substitute in? Sometimes one form is way more helpful than another. We're going to talk about that in a minute. But once you do make a good substitution, the whole purpose for this is your new differential equation will be with u and x, or perhaps with v and y. And then you can solve by separation of variables. You're going to go right back up to where we started this chapter. Now, knowing which substitution you want to use, because you could see in yellow we've got y equals ux, x equals vy. If the dy function is simpler, let's keep it simple. Use the y equals u times x. If your dx, what your function in front of dx, or m in other words, if that is simpler, then let's go ahead and have x is equal to v times y. That's a good rule of thumb. I think we're going to see what is happening right now. Let's do a problem together. Of course, we've got this example 1, and we've got our m right here, and we've got our n right over there. The first things first is we're trying to solve this. Of course, we would like to go ahead and show that we have a homogeneous function for m and for n. So m, if I were to substitute in a tx and a ty, and again, we're looking at our m is just x plus y, I hope you could see that would be tx plus ty. And we could factor out a t and have t times x plus y. Another way of saying that is we've got t times m. What happens as I substitute in a tx and a ty into n? Well, n only deals with this x here. So nice and simple. Very, very simple. We're just going to have a tx. And x, of course, was n itself, so we have t times n. In other words, we have t to the first times n, t to the first times m. We have a first power for both of these degrees, so therefore we have a homogeneous differential equation. So that's a good thing to check, that this method would be helpful and useful. Now, as we're looking here, you might wonder which differential is simpler. And we can definitely see that dy is simpler. So a good rule of thumb then is to say, let's substitute. Remember, we had two choices, yellow or blue here. Well, it looks like dy was simpler, so we could let y is equal to u times x. Good practice right now. We could go ahead and take a derivative real quickly with differentials. We could have a dy. Using the product rule, we'd have a u dx. And then we could say x times du. Now, the whole reason for doing all of this is that right now I can come back to the original problem and rewrite it. I can say, well, let's see, I had an x plus, well, instead of having a y, I'm now going to replace that y with ux. And then I have dx. And then I've got my x for my n right here, but my dy, you can see, my dy is going to be a u dx plus x du. Now, at first glance, you're probably looking at this thinking, did this actually help us out? It did, actually. It might not appear that way just yet. But this differential equation is about to get to be separable, if you can believe that. Something that I like to do at this point, and I encourage you to do this too, you can go ahead and, if you have to distribute, especially with that differential that you just took note of, we can go ahead and multiply through it. We get a ux, or an xu dx, and then we'd have x squared du. And that's just like a momentary pause. But I guess the other thing that I'm really trying to point out to you is that we've got this right here is going with dx, and this ux right here also is with the dx. So tell you what, we can do a little arranging at this point. We can slide over and say, you know what, I'm going to take this thing and bring it over here. A ux and a ux would add up to a 2ux, so I'm not even going to break through with the distributing. I'm just going to see that I could slide that other ux in. We've got a 1ux and a 1ux. That makes a 2ux. And then how about over here? Well, if I got rid of my ux, I just have an x squared du. Now, at this point, according to what we just wrote in our notes, we should be able to go and separate. And let's start moving things around. I'm going to keep this x squared du over here on the left side, and I'm going to bring this other stuff to the right. And I'm also going to simultaneously say, if I brought the whole thing over, I'd really just put a negative out in front of it. Tell you what, I'm also going to factor out an x as I'm doing that. So I'm combining a couple of steps right here. I hope you can see what I just did. Move that whole parenthesis with the dx to the right. That brings a negative out in front of the parenthesis. Simultaneously factor out an x. You can think, well, why in the world are we doing that? Well, guys, we need to separate our variables. We're going to have to separate. So, I have a du over here. I'm going to divide both sides by a 1 over 1 plus 2u. Simultaneously, I'm going to divide by x squared. And guys, if you are dividing by x squared, if you had negative x over x squared, I think you would agree. You just have a 1 over x. So this is what we mean when we say that it's separable. It only would take a moment to see that. And then we're going to integrate. And I'm going to continue my work off to the side here. As we integrate, you're going to have to reverse the chain rule. You'll have 1/2 natural log of the absolute value of 1 plus 2u. And on this right-hand side, we're going to have the negative natural log of the absolute value of x. And of course, we could even put in a constant here. Tell you what, you might as well even multiply by a 2 to get rid of that. And that would clean things up pretty fast. The only problem as we're moving ahead is you're probably noticing that we don't have a y in here. This is where we're going to go back to where we had actually substituted. We substituted y equals ux. That's what started this whole thing out. That means that u is also equal to y over x. So as we have separated, as we go ahead and, we have separated and integrated, we can go ahead and get a little bit of help substituting back in. So now I've got a y in there, and you might guess we're going to exponentiate both sides. You're going to have 1 plus 2y all over x. Right here, x to the negative 2 is 1 over x squared. That's the cool thing right there. E to a power is going to be another constant. I hope you can see we're going to come up with this. By the way, forgive me, I forgot some absolute value on the left. We're going to very quickly get rid of the absolute value and get a plus minus over here, but a plus or a minus, a constant, is really just a constant itself. And at this point, tell you what, we can subtract a 1. And you can even bring that x squared down over here. Then what? Tell you what, let's multiply by the reciprocal real quickly, multiply by an x all over 2 here, multiply by an x over 2 over here. What are you left